Hello, and thank you for joining me. My name is Tom Knauer. I'm with Balluff. I'm an industry manager for condition monitoring and various other business topics. Today, I'm going to talk about the topic of condition monitoring, boost efficiency and reduce unplanned downtime, how to move from reactive to proactive maintenance. So let's get started. We'll have an agenda of several different topics. We'll talk a little bit about what's going on in the manufacturing industry and the challenges that are faced by manufacturers. Then a little bit about how failures occur and the related maintenance approaches, what people are monitoring in the factory, potential solutions, then some case studies and real-life examples, and then finally some hints on how to get started. So let's move forward. There are many challenges going on in today's manufacturing world. Some of these have existed for a long time, some of them are relatively new. But in general, manufacturers face a variety of things that are making their lives increasingly challenging and difficult, but also present opportunities. We see things like the changing workforce and labor issues. We see inflation and rising costs. We see tariffs and trade conflicts, shorter supply chains, increasing competition, drives to reduce costs, and so on. This means that manufacturers really have a strong need to do several things to improve their efficiency. First of all, they're bringing more automation into the workplace, digitalization, robotics, and other technologies to help them compete. They need flexible factories to adapt quickly to changing situations, whether it's customers asking for various different products made on the same product line or adjusting to competitive situations in rising and falling demand. Smart devices are needed to tell manufacturers what's going on the shop floor, and they need to be communicating to each other and to control systems and to higher level systems in the factory and beyond the factory. And then finally, software and AI are driving all this data that's coming and helping the factories run more efficiently and more carefully planned. This means manufacturers must be more efficient, they must get more out of their equipment and improve overall equipment effectiveness. So, in terms of overall equipment effectiveness, or OEE, what are the goals? We typically see 4 key attributes that our customers are working on and trying to focus on: reducing scrap and improving quality, improving their overall asset utilization and machine utilization, reducing unplanned downtimes and small stops, and then finally, just reducing overall manufacturing and supply chain costs. Condition monitoring and predictive maintenance can help address most, if not all, of these topics in some ways, and can really help manufacturers attain their goals in improving overall efficiency. When we talk to customers, we find that they overall have one big challenge, and that is unplanned machine breakdowns. That's by far the most common issue that they talk to us about. Related are several subtopics, including things like the long time to repair machines and replace equipment, find parts and components, and so on. Often things that fail are in hard to reach places, maybe locked behind a control cabinet or up high on a machine or in a remote site. And then finally, most manufacturers are being driven to more increasingly use the data that's coming off their machines and improve overall efficiency, equipment efficiency, and tie into their broader industrial Internet of Things systems. This really means, in the end, that the lost production and lost capacity and lost machine availability means lost revenue. Whether we're talking about making cars or food and beverage, life sciences and pharmaceuticals, or semiconductors, this is the common focus across the board to avoid that lost downtime because of the costs associated with it and the lost revenue. So how do things fail? We'll talk a little more about failures and maintenance approaches. In general, we find that there are 2 different types of failures that occur on a broad basis in broad categories. This data has come from a variety of different sources over time and seems to confirm over and over that the ratio is about 20% of failures are age-related. So if we talk about age-related failures, there's a clear correlation between the age of the asset and the amount of failures that occur. As it gets older, it's more likely to fail. If we think about a car, for example, as it gets older, the body rusts out or the tires wear out, the engine wears out, or so on, based on more and more usage. What's interesting, though, is that 80% of failures in the factory are not age-related. These are more evenly distributed across the life of the asset. It could be an equal probability at the beginning, middle, and end that this type of failure occurs. And these include things like improper design and installation, operator error, quality issues, machine overuse, and so on. Likely, in most cases, a preventative maintenance approach will not solve these problems. And we'll talk a little more about that in a minute. So if we, again, use the car example, you get in a car crash. That can happen equally likely at the beginning, middle, and end of the life cycle. Or you run the car too hard and it breaks down because you've driven too fast or above the specs. These kind of things are the more random, non-age-related errors that happen and failures that happen 80% of the time. So how do we address these, and how does this relate to how machines fail and maintenance approaches? We've categorized 4 basic different maintenance approaches. Starting at the bottom with reactive approach. This approach basically is a run to fail type approach. You only fix things when they break. It means very low upfront maintenance costs, but potentially very high costs of that failure, whether it's the lost production time, whether it's the cost to repair that part, or so on. The next more sophisticated approach is preventative maintenance. This is very common, like changing the oil in your car or changing the tires and so on. You do this at regularly scheduled intervals, and you're trying to get ahead of these failures. It's pretty good at addressing the age-related failures because you're trying to get ahead of that age pattern, but they're maybe not as good as addressing the non-age-related failures. The next more sophisticated approach is called condition-based approach. You're starting to monitor the assets using sensors, and you're asking the sensors to get the data that will help you determine an impending failure is about to happen. It definitely improves significantly the likelihood that you catch a failure before it happens. It does cost more upfront, but in the end, the cost of the lost downtime, the cost of the failure, and so on can be dramatically reduced. And then finally, the most sophisticated approach is predictive analytics. This takes the data from the condition sensors and not only looks at them at any given moment in time, but starts to look over a time series, look for patterns that start to emerge, look for cycles that start to emerge, that you can start to predict far ahead that a failure will occur and schedule the repair and maintenance long before the failure occurs. Higher upfront cost, but much more reduced, lower later cost and cost of the failures because you're preventing that failure far before it happens. So the goal here with condition monitoring and predictive maintenance is to move up from more reactive approaches to more proactive approaches. And again, work on taking an approach that allows you to predict the failure, deal with that failure on your own time schedule, and potentially shut that failure down before it happens and reduce the cost of that and reduce the disruptions to your facilities. There is one other approach that's been emerging in the industry lately called prescriptive. It really is taking the data out of the condition-based and predictive systems and using that not only to predict the failure, but then also to write a prescription as to how to deal with that failure. So if your asset is going to start to fail in a certain way, the predictive or the condition-based system determines that. It can then also give you a prescription of how to deal with that and have your maintenance team get the steps in sequence into how to take care of that potential failure before it happens. So how do we tie this together in terms of the failure modes and the maintenance approaches? Well, here we have our 4 basic maintenance approaches. And when we look at the age-related failures, really the only one that doesn't deal well with an age-related failure is reactive because you're letting the failure occur and so you're not getting ahead of it. Preventative generally can address those. Condition-based and predictive analytics can also address those because they're starting to see that failure occur, see the asset deteriorate with age, and can address that. What's more interesting is how non-age-related failures are addressed. So again, reactive doesn't deal with those. Preventative likely also does not deal with non-age-related failures, those failures that occur due to incorrect installation or running the machine too hard. But condition-based and predictive analytics can start to give you the insights that that failure is about to happen and help you deal with that in a more proactive manner. So let's now use a real-world example. This is about a year's worth of vibration data on a machine. We can see that generally it started off pretty smooth, and then in the end, about a year in, the red line starts to show a failure pattern, and that's where the asset breaks and you have a complete catastrophic breakdown. So how would the different approaches address this? First of all, reactive. Reactive, of course, doesn't do anything until you actually have the failure happen. So you're really letting that failure happen, letting things break, and you're going to have to deal with the consequences of a major catastrophic failure. Preventative maintenance has regular intervals. In this case, we're doing quarterly maintenance. And depending on the timing and depending on what you're doing the preventative maintenance on, you may or may not address that reactive potential failure in a proactive way and relatively get ahead of it. It could be, however, that is in this case, you did the maintenance a couple months before and maybe you didn't do it at the right time or didn't do it at the right part of the equipment, and therefore the failure went to catastrophic, even though you did implement a preventative maintenance approach. Condition-based monitoring starts to look at the data coming off that machine. In this case, we're looking at vibration data. We've set a limit, and once the vibration exceeds that limit, we send an alarm to the operator and to the maintenance team to say that there's something happening in that asset and that it needs to be addressed. In this case, we set our alarms so that it turned out that the vibration hit a certain level about a week or 2 weeks before the catastrophic failure would have occurred. And so we did have some warning and some time to address that failure. Relatively short time, but we did have some time. The other thing here, though, that's important to note is that we had several spikes that almost exceeded that alarm level, but probably didn't. And so setting that alarm level is a little bit complicated. You can do it based on experience with the machine, but there's also ISO standards that are available to help guide you. And there's other experiences that you can use to set that at the right level. So perhaps in this case, if they'd set it a little bit lower, they would have probably had almost a month's worth of warning ahead of time that that failure would occur. The most proactive approach is predictive maintenance. It looks at all the data coming off that machine, and in this case, again, the vibration data over a significant period of time. And we can see that the pattern has started to increase, especially after about 7-8 months. And that's when the predictive system starts to kick in and starts to look at that something is starting to occur and can generally give you probably, in this case, a month to 2 months worth of warning ahead of time that you need to do something, need to send somebody out and replace a part or do something on that asset. So again, this gives you a good overview of how these 4 different approaches interact and how they might deal with failure on a machine. So what should we monitor? There's a variety of things going on in the factory, and generally we find that in your production system, and this is kind of a typical layout, there's a lot of different places where people might monitor. We work with customers that are doing things like monitoring conveyors, monitoring motors on machine tools, fans that extract dirty air, control cabinets even, cranes, hydraulic power packs, robots, pump stations. All these are good candidates for condition monitoring depending on how critical they are to your operation. We'll talk a little more in a minute about determining the criticality and which assets are the most important, which ones might be the most disruptive to your production that you want to start monitoring. But in general, the goal is to reduce the machine downtime by monitoring the most critical mechanical components and the machines and the overall factory to improve your productivity and improve overall equipment effectiveness. So what do we have in terms of real life experience that we've gathered? Well, we have data from PMMI, the US packaging organization. They did some surveys of OEMs and end users on the components that are most likely to cause downtime. And then we've done our own data gathering on what our customers are monitoring. We can see there's a variety of things here, but generally the most common things that are monitored are things that monitor some kind of, involve some kind of motion. So motor drives and gearboxes, servo motors, induction motors. And from the PMMI side, from our side, motors, pumps, spindles, fans, gearboxes. Again, motion is involved in 80 to 90% of the applications that are being monitored right now. What are you monitoring on those moving assets? Well, there's a bunch of different indicators that are commonly looked at, but you can see things like temperature, vibration, magnetic field, current, speed, pressure from the PMMI side, and from our side, vibration and temperature are generally the most common ones. We find that vibration is involved in 80% of the monitoring that's out there because it's fairly easy to monitor. There's a lot of different vibration monitors available, and it's a really good indicator that something's starting to go wrong on things that are moving. So let's talk a little more about the theoretical approach here. This is what's called the PF curve. It's the potential functional failure curve, and it's the difference in time between the potential failure and the actual functional failure of the asset. This is not to scale, it's just a rough example of the life cycle of a asset failure. So you install the asset, at some point it starts to wear out, starts to fail, and then different indicators emerge depending on the asset that tell you and might give you some pre-warning until you go to the catastrophic failure. So if you wait and just take a reactive approach, you're going to start seeing things like smoke, it's going to get hot to a touch, parts are going to come loose. So that's the very reactive approach, the fault domain. In more proactive domains, we have things like using ultrasonic measurements, vibration analysis, oil analysis, temperature analysis, pressure and flow, those things. Those start to get into the proactive and the predictive domain, where you can have some data coming off that you can utilize to anticipate that failure before it actually happens, before smoke starts coming off, before things start to break catastrophically. And again, these emerge at different points of time. One of the other things to note is generally those indicators that you might measure earlier can often be a little more expensive. The sensors and the systems to do that are a little more expensive than the ones that wait later. But there's a trade-off there, again, between detecting earlier and reducing the overall cost of the failure versus using a more expensive system. We'll talk about that in a minute. This is how it also ties to our different maintenance approaches. These things like ultrasonic energy analysis and vibration analysis and oil analysis are more in the predictive maintenance approach. In the middle, pressure and flow, vibration, and so on are more condition-based. And then again, we mentioned the reactive approach. So let's talk now about solutions. Why do these concepts matter? Well, the goal is to detect more quickly, so to move left on that PF curve so that you have more time to deal with a potential failure. We want to reduce the cost of the monitoring of that failure, to catching it, so that it's more financially viable and the ROI is better by detecting sooner. And we want to move more to a proactive approach. So by working with Balluff, we are really trying to help customers detect more quickly, reduce the cost of that detection, and taking an easy, low-cost, proactive way into condition monitoring and predictive maintenance. Now let's talk about which approach is best. Well, it really depends. It's kind of a little bit of a broad answer, but the fact is most factories have a wide variety of equipment and assets installed in their facility. Some are very critical, some are less critical. Some would be very expensive to monitor failures on, some would be less expensive. So really, we look at the different approaches and we take a unique profile for each asset and the cost of detection. So in this case, we have a cost of prevention. So the cost of detecting early can be relatively high compared to waiting and taking a very reactive approach. On the other hand, the cost of that failure, as you wait longer and longer, can become more and more expensive. So each asset has a unique trade-off curve between the cost of prevention and the cost of the repair. Some assets, the cost of prevention, the cost of installing sensors and detection systems could be very low because it's maybe very simple to monitor that. Maybe a simple vibration monitor can detect that and it's very easy and simple to install, whereas the cost of the failure can rise very rapidly. And so it's going to be very beneficial to install a preventative or predictive maintenance system. Other assets, maybe a run-to-failure approach is more appropriate. So we have a very high cost relative to the cost of failure. And so we want to think about maybe we even take on some of those assets a run-to-failure approach. Think about a small fan that's blowing cool air onto a part of the production line. Maybe the fan costs $10. A condition monitoring system might cost thousands of dollars. And if that fan fails, you're not really going to shut down production, but it might get a little warm in the area. And it might be better to let that fan fail and just have a couple extras $10 fans on the shelf. So that might be an example of a run-to-failure approach that's appropriate. But in the end, again, the facility is going to have a variety of different curves for each different piece of asset, and you're going to see many different approaches that might be appropriate. And so in some parts of the factory, a run-to-failure approach might be appropriate for certain pieces of equipment. Others, a very proactive approach might be best. And in some cases, a preventative approach, a regular maintenance interval approach might be best. So how do you prioritize? How do you decide which approach to take? Again, that $10 fan, maybe not so critical. The $100,000 piece of equipment that if it shuts down, you lose production for 3 days, might be more critical. How do you decide that? Well, there's some tools for criticality analysis. There's a variety of these out there, but they help you put a numerical value on the different parts of the operation and assess and rank the different pieces of equipment. So here's an example of a spreadsheet type approach, Excel type approach, and you're looking at things like the cost to repair, the cost of the spare part, the cost of lost downtime, and various other factors that are important to you that you can customize these to help you rank the different assets in the factory. It's similar to a safety risk assessment, but a little bit different. And again, here's another different approach where they're looking at the probability and the severity of that failure. And they're saying, for example, low probability, low severity, you probably don't necessarily need to worry about that asset. Whereas high probability of failure and high severity, you probably want to address that piece of equipment first. And then finally, as I said, there are many different approaches. You want to pick the one that seems to work best for you. This approach here looks at the loss of cost production, the cost of repair, the impact on safety, and the frequency of that failure to kind of put together a numerical value. What you're trying to do is really rank the equipment in your factory from least critical to most critical and start to think about a condition-based or predictive approach on the most critical assets to start. So how do you gather the data? Well, there's a variety of different types of sensors and tools out there, starting with basic condition monitoring sensors. These are dedicated sensors that do things like monitor vibration and temperature. Sometimes they have extra functionality. In this case, we have a sensor that also does ambient pressure and relative humidity. And then enhanced features such as FFT, fast Fourier transform data, which allows you to look at the frequencies coming off the vibration and analyze them in a more detailed, specific way. And we'll talk about that in a minute. It's very good for bearing analysis, very good for complex frequency waveforms and breaking those down into the different elements and looking at the different frequencies based on what's happening and analyzing those rather than just overall vibration, which may be masked. There's smart sensors out there that have a core function that is normally sensing things like photoelectric sensing, inductive sensing, and other functionalities. So they have a basic function, but built into the sensor is additional capability to monitor temperature, vibration, inclination, health of the sensor. So it's a dual purpose sensor. It may not be as focused on the condition monitoring data as a dedicated condition monitoring sensor, but it offers good enhanced capability where the data is necessary to have in addition to the standard function of that sensor. We have the normal process monitoring sensors for things like pressure, temperature, flow, and so on. These are really good on things like hydraulic power systems and lubrication systems where you're wanting to measure flow and pressure of the hydraulic fluid and so on in the system. And then finally, we have smart electrical devices like power supplies and contactors and so on that give you back information on their health, on the power usage and so on, that can also add signals to this whole system and data that you can use to start to get more into a condition-based and a predictive approach on your system. So the key thing is that monitoring multiple signals can really help you. You need to think about what's the right signal to gather that will help you get an early warning of these potential failures. It's not always vibration. It might be pressure and temperature and flow. And often we are finding that gathering more than one signal can give you better insights into a potential failure. So not just measuring vibration, but maybe vibration and temperature, or measuring pressure and flow on a hydraulic system can give you a little more insight into a potential failure coming rather than just measuring one indicator. So how do we move the data now from those sensors? You have a variety of your different sensors. If you've selected the appropriate ones to find those failures or proactively address those failures, how do you get the data to where it's needed? Well, there's a variety of places that the data is used. So it can be used directly in the machine control. You may want to shut the machine down right away when you exceed a limit. You may want to be moving it into your SCADA and MES system for visualization and display, or up into the cloud for deeper analysis, looking at those longer trends for predictive maintenance, or just basic visualization on a handheld device or an operator interface to give you signals, or it may be that you're looking to use the data in multiple ways. There's a couple different ways to move it. Traditionally, we've used interface blocks. We tie the sensors into, in this case, a block that gathers the data. It's connected by Ethernet, industrial Ethernet, to a machine control system, to a SCADA system, and now they've added the capability in many cases to take the data from these blocks directly into the cloud through the variety of different types of IIoT type protocols and interfaces. Another way is to have a dedicated edge gateway device. In this case, it's what we call a condition monitoring toolkit. This has added capability not only to take the data from the sensors themselves, but to do a little bit of pre-processing and then to communicate it up into the cloud and where it's needed, but also some software built in for plug-and-play visualization so that you can very quickly and easily get that data up onto a screen, look at trend patterns, look at dials and alarms and so on, and get your system up and running. This is a system that works very nicely in parallel to a normal machine control system. It doesn't necessarily affect then the machine control system, and you can implement it very quickly and easily onto existing legacy machines or new machines. So let's talk about the different ways we gather the data and then what kind of solutions providers are out there. We have a wide variety of people out there providing condition monitoring solutions, ranging from people who just provide sensors and gateways to people who come in and do it for you and come in on a monthly basis, quarterly basis, and do the monitoring for you and look at it with specialized, highly specialized equipment. There's proprietary companies, and then there's people who come in and do it as a service. So they install the sensors for you, they monitor it for you, they set the alarms, and then they notify your team. So these are a variety of ways that you can implement condition monitoring and predictive maintenance. Generally, these are more in-house solutions where they're utilizing existing equipment and you're buying the equipment from the suppliers and installing it in-house, versus these are more outsourced. The condition monitoring as a service is that the provider does it all for you. There's also a variety of ways that these approaches take you in terms of the controls architecture. So how does it tie into your control system, your SCADA system, your cloud system? How do you gather the data? How often do you gather it? Are you using it in real time? If you need that data in real time to shut down a machine, generally you're going to look at sensors and sensor gateway solutions. Condition monitoring as a service is not going to do that as well because it's done gathers data on a time-based interval, maybe every minute, maybe every 5 minutes, so it's not truly real time, whereas these can gather it instantaneously or almost real time. There's different amounts of effort and cost required by the customer. The data is owned by different parties in this whole spectrum and so on. So depending on your needs, you may find that owning the equipment and the data and a one-time fee, upfront fee, like using a sensor and sensor gateway may be more appropriate, or if you want to outsource this, using a condition monitoring service may be more appropriate. So how does this all work? Again, condition monitoring as a service, there's no upfront investment, it's easy to do, but it does require that you pay a subscription fee, and there's usually cyclical data gathering every minute, every 5 minutes. It's not real time, and there's some other things, challenges associated with that, so that's one approach. Another approach is route-based maintenance. This is where an outside company comes in every month, every quarter, and so on, often used for highly specialized equipment like power generation turbines and so on, where you're looking at very precise measurements, ultrasound systems, vibration, high frequency vibration analysis, oil analysis, and so on. These are often only able to be done with very specialized, very expensive equipment that to install them permanently would be not cost effective. So it's a very good approach for high value, high expensive equipment where the vendor has very specialized knowledge about that equipment. But the challenge is it's often a high cost per visit, it's very cyclical, it's not real time, and so on. And then finally, sensor and gateway solutions. They're real good at continuous real-time monitoring, can be tied directly into your control system like any other sensor. There's a wide range of measurements possible, whatever sensor you want to apply, whether it's a vibration sensor, whether it's pressure or flow. The data can be easily integrated into your system. You own that data. On the other hand, the initial investment up front is relatively high. Generally, either you or systems integrator are going to have to install that system. So let's talk about some case studies real quickly, real life examples. Bearing monitoring. So we have a situation where a customer is looking at monitoring bearings. Bearings have different components that vibrate at different frequencies. So if you're just taking the raw time series vibration data off that, you may not detect a failure because the different frequencies of the different components may mask each other out in terms of that failure, and that you only really see the vibration spike very late in the failure. What happens with a bearing is you have the inner race that vibrates at a certain frequency, the ball bearings vibrate at a different frequency when they're failing, and then the outer race vibrates at a different frequency. Using a fast Fourier transform analysis, you can break out those different frequencies and monitor those specifically. So breaking that time series vibration data into different frequencies and monitoring those and setting alarms based on those is potentially a much more effective approach. Not all vibration sensors have this capability, but when you are looking for monitoring bearings, you can buy and find sensors such as the Balluff BCM that have that capability that allow you to monitor the bearings and break down those frequencies and detect the failures more quickly. Here's another case study of a spindle monitoring on a woodworking machine. Here's the spindle motor and the vibration sensor, and then you have the condition monitoring toolkit that is gathering the data off of that. This allows the customer to monitor the problems with any problems with the spindle, problems with cutting tools, and so on, and allows them to proactively make tool changes or spindle changes before there's a failure. The customer that we were working with makes machinery for working on wood window frames, and they'd had some customer problems where the failures caused significant downtime, and they were able to prevent that going forward once they installed the condition monitoring sensor and the condition monitoring toolkit. Another example is hydraulic dispensing system, spray dispensing system. In this case, the customer installed a couple of smart sensors, pressure and flow sensors and temperature sensors, because when they're spraying, they need to make sure that the pressure on that cylinder is uniform and is not interrupted due to problems with the fluid and so on. They were able to detect potential failures ahead of time with the hydraulic system, part of that system, and shut down and do some monitoring, change out some filters, change out the hydraulic fluid before they had a catastrophic failure. Another one is paper-based packaging machine. They're looking at vibration on the spindles here and looking to detect that something is going wrong with the winding process of the paper and that there's no tears, because they can start to sense that there's excessive vibration if there's a tear in the paper or some other problems. Controls cabinet. This is a little bit of an unusual one. We have several customers in the food and beverage business. They have to wash down their whole area multiple times a day and have had problems where the control cabinet wasn't quite locked and closed, and they had ingress of the cleaning fluid, the hot and cleaning fluid, into that area and destroyed electrical equipment. They have a temperature and humidity sensor in there that detects the increase in humidity and temperature if the door is cracked open, and sends an alert and alarm that tells the operator to stop the cleaning process because the door is cracked, and avoids destroying the electrical equipment in the cabinet. This is on a compressor system monitoring for vibration. In this case, the compressor runs 24/7, and they need to know ahead of time if it's going to fail so that they can take it offline during a normal downtime and address the compressor problems, whether it's on a bearing or on the compressor motor, and shut that down and do the maintenance proactively before they have a catastrophic failure. So how do we get started? Well, there's several different steps. We had an article that was published by Control Engineering magazine that simplified the process fairly quickly. First of all, conduct a criticality analysis. We talked about using Excel or other tools to rate your most critical assets. Which ones are most important to your bottom line, which ones would have the most effect on your production. Then identify the potential failures of those assets. How are they going to fail? Does the manufacturer of that piece of equipment have recommendations? Have you experienced with that piece of equipment? Do you know other people who have similar equipment that have it installed? Find out what ways that might fail. Then identify the technology. Do you want to measure vibration and temperature? Do you want to take that data out of those sensors directly into your control system, or do you need an edge gateway device? What's the best approach? Do you want to take condition monitoring as a service approach, have somebody else do it, or do you want to keep control of the data and the equipment? And then finally, install analyze, test, and make sure you're monitoring the right things. Are you now starting to see the data and the signals show you that a potential failure is occurring and that you're able to prevent those failures, or do you need to refine and start monitoring other pieces of the equipment, gather other signals? And then you can repeat the cycle and expand. So some hints here on getting started with your first project. Start with a small pilot. Identify a piece of equipment that you'd like to monitor and start to install a system to test it. Does it work? Then get buy-in with the maintenance team and the leadership team. Explain the benefits of this process to them. Document the positive impacts of the changes and then discuss them with the rest of the team and your colleagues. And then finally, expand it once you've had success with the first project. The key thing here is that condition monitoring and predictive maintenance are going to give you warnings about faults, failures, and downtime, and make it possible for you to schedule the repairs and maintenance when it works for your schedule, rather than have the machine schedule it for you when it's at the worst possible time in the middle of a big production run. So with that, thank you for listening. I hope you will take away some lessons here in terms of moving from a more reactive to proactive approaches, and that condition monitoring, predictive maintenance can really help you improve your overall equipment effectiveness, reduce those unplanned downtimes, and generally be more efficient in your factory and facility. Thank you very much.